So good morning, everybody, and welcome to my talk. This morning, we'll kick off with a performance session. My name is Ionut Balosin. I'm software architect. Apart the software architect for Luxoft, I'm working for Luxoft company in Bucharest, Romania. I'm also technical trainer on Java performance and tuning and software architecture topics. What would be the agenda, how I will structure the information for this session? It will be based on layers. So we'll start with the design principle layer. We'll discuss what are the guidelines specific to that layer, but we'll study everything from a performance perspective. So the aim is to study each of these and to associate them with some performance. What are the performance connotations? We'll get down into the tactics, patterns, algorithm, data structures. We'll go even more down into the OS and hardware. So we basically touch everything. Of course, since we move a bit down, the layer of the complexity becomes more and more. Since we start with a layer which is an upper layer, the abstractions are higher. This is my performance model because not all the tactics and guidelines, patterns that we will iterate through during this session are suitable in all the contexts. In regards with that, I've created my latency model. So at the bottom of the latency model are mainly projects where the performance is not as architecture-specific requirements. In this case, you shouldn't apply all the things that we'll discuss today. If your project has a bit of affordable latency, for example, there are hundreds of milliseconds, of course, you can apply on top of the bottom ones some others to meet that affordable latency, whatever it means. And things might be even challenging if you are moving up to the top of this pyramid, if you are touching the low latency or ultra low latency level. And the aim of this talk is to iterate through all of the layers presented before and to map these layers into this pyramid to see how the things are going. This being said, before to kick off, let's fix what is performance from a theoretical standpoint. And for today, I took a very basic definition from software architecture. Performance is nothing else but just satisfying some time requirements. If your application in terms of response time, in terms of throughput, satisfies the initial SLAs in terms of time requirement, you can say it's performant. Now there are projects where these requirements are more and more stringent. For example, you should be under 1 second, several milliseconds, tens of milliseconds, and so on. If that one satisfies performance, it's always the performant application. If you don't have performance, you are in the affordable situation, or in the first case where the performance is not an SR. Recently, I wrote an article for the InfoQ, and here is also an advice for you to stick with the terminology, with the term, basically the quality attribute. Performance is not a non-functional requirement. Performance and all the other ilities like security, availability, scalability, and so on are quality attributes. And here in this article, I provided my reasons around that. And the recommendation for you is to stick with the quality attributes, to not use any more non-functional requirements. Okay, all of this being said, let's touch the first layer which is for the design principles. And in terms of this is the cohesion. What's the cohesion? It's basically the degree of which elements belong to each other or together. And I chose this color representation to illustrate that, for example, if we have a class or a package or a component, whatever, and you have objects that are not used each other or between, they are not working with each other, it's better to segregate them. Why is that? Because seeing from a performance standpoint, it's always good for also the CPU, the instruction cache, if those are instructions, if you refer to the data also for the data caching. So you are more CPU friendly if you segregate and design your classes, your components, and so on, based on a high cohesion. The second one, it's basically an example. We are using properties, places with properties. For example, the property placeholder, the property bag, class of constants, all these kind of things. And we put all the properties and we refer all of these properties across many colors. So each color, imagine one color being a thread, right? Request a property at the moment. The thing is that each color needs to add in the CPU cache that property, and that might call a miss, a CPU data miss, which is not good. The advice is to keep the properties closer to the context they are used, closer to the color, and not to share them across multiple colors. Abstractions, it's another one, which says basically the idea with abstraction is not to create another semantic layer which is more general, but on the opposite, to be more precise. For example, we have this hierarchy, the shape, and with three implementation. The thing is that in Java, this is an example from the polymorphism perspective, and how it is resolved via during the runtime, it's via virtual calls, and there is a vtable. So we pay the cost of the vtable during the runtime to reach the target implementation. And the thing is that if we are using two and starting with the third and the second, the third implementation, the cost is higher and higher. The idea is to minimize this kind of abstractions because they have a cost during the runtime. Complexity, it's another one, which means basically the number of linear independent paths that your code can follow during the runtime. More paths you have in your code, less predictable you are for the hardware, because the hardware cannot guess, for example, what would be your next option in terms of statement which might be executed. For example, in Java, the just-in-time compiler can optimize if you follow on hot paths and put some uncommon traps for the others, but still you have to pay the cost if that uncommon traps are hit. So the advice is to minimize and to be more predictable, to refactor your code in order to minimize the cyclomatic complexity, because you will help the hardware predictors as well. Another guideline in terms of complexity are the algorithms complexity. We learn from schools that complexities are good, and we are keen on minimizing the complexities in our algorithms. But the question that might arise, is it all about the bigger complexity? Because having a lower complexity implicitly provides a lower service time. And for this, just to study and to illustrate how the things are going, I took two examples. The first example is I took a two-dimensional array. It's a matrix, and I traversed that matrix, a row traversal, keeping the same row and changing the columns. And the second case, it's the opposite. I kept the same column and I changed the row. The code is pretty simple, and in both cases, there is the same complexity, which is a cubic complexity. I took both of these cases and I studied them with different metric sizes, for example, 64, 512, 1024, 4096. And as we can see, in the row traversal, I always got a better throughput because there is number of operations per microsecond. So it's always better to traverse a matrix using the row fashion. The question is, why? Because we need to understand what's going into the hardware. And to understand that, I took the last case, 4096 by 4096, because this one, it's quite interesting. It has about one order of magnitude between the results. And let's see what happens. To be able to profile that, I was going even deeper in the hardware level, and I sampled the hardware profile counters. And in this particular case, I illustrated, for example, I was focusing on illustrating the data cache loads and misses. For example, I took L1 last level cache, the third one, and translation leukocyte buffer, the TLB one. And as you can see here in the column traversal, there is a big discrepancy as well in terms of cache misses. But still, we don't really understand why it's there. So we need to get back and make a parallelism with the theory, why it really happens. Because it might be an answer for the question why the throughput is lower, but still we don't have the big picture. So if we go even more in the hardware, and let's see how it goes. Let's suppose we have the first case with a row matrix traversal. And in this row case matrix traversal, the first one, when you hit the first element, there might be a miss for sure, because that thread which requests the first element doesn't have in its local cache the element. But once you request that one, it is retrieved from the main memory, and it is laid out in the first cache line. The first cache line, it's around 64 bytes in the majority of architectures. So in this case, once you hit the first element, you automatically, because there is a matrix and there is a continuous memory layout, you'll have all the elements next to it layout in the first level of the cache. And when you request the second, the third, the fourth, you will have everything on the first cache line. Because you traverse the matrix via a predictable pattern, the CPU can guess and retrieve automatically the elements in the next cache line. So the number of cache misses, it's even less, so it's quite efficient. But what happens in the second case, where you have a column traversal? When you have a column traversal, the first is the same. You pay the cost of a miss, and you retrieve the entire cache line and use just one element. Because for the next element, you have to do a striding and to skip the entire line, the entire row for the matrix, and move to the second row and retrieve the second element for the first column. So that's why you basically, in the second case, it's very, very inefficient, because you always fill in the elements in the CPU cache line, and for each cache line, you retrieve just one element. That's because my matrix, it's huge, and the first row, it's bigger than the first CPU cache line. This is an explanation why we get better throughput in case of row traversal and a worse one in case of column traversal, and why there are so many cache misses. Which concludes me that on modern architectures, the service time is greatly impacted by the CPU caches, the way the data structures are laid out in memory, and of course the way you traverse them. These are and of course the dependencies might be. These are the key factors. Big O complexity might be a win in case you deal with very huge data sets where the CPU caches doesn't help you a lot. But in all the other cases, if you follow a predictable pattern and your data structures are compacted, you will benefit of the CPU caches. And the recommendation in terms of complexity is to reduce the code footprint to be as small as possible. Why? Because it has an implication in the instruction cache. Nevertheless, there are some optimizations also ahead of static compilers and just-in-time compilers, for example, the ones from Java, just-in-time compiler, and the other ones ahead of time, do a lot of optimizations, especially in terms of loop unrolling. They unroll your loops, and they do a lot of inlining, so they change the footprint of your code, and this might impact as well the instruction cache. So you should be aware of that optimization as well. The second layer is in terms of tactics, patterns, algorithms, and data structures. Let's start with the caching. Caching is the most straightforward one that we should use. We should apply because it optimizes, for example, in some context, our requests, and we have a better response time. But when we use caching, we have to take care of the data patterns because there are slightly different tactics. If you use, for example, read-write true, or if you use write behind or read ahead, there are different tactics that you should apply on the data patterns. As well, you have to pay careful what's your eviction algorithm. For example, if it is least recently used or last frequently used, stuff like that, because there might have an implication in the cache misses as well. So if you profile a cache and if you figure out that the number of cache misses is higher, maybe something it's wrong in the cache internally. It is improperly configured. As well, the fetching strategy is important because you can use, for example, a prefetching strategy, an on-demand strategy, or you can let it to be predictive like it is in hardware. Depending on the data, if the data, for example, it's more static than dynamic, probably the prefetch one, it's a better approach. And the last one, the topology of the cache impacts a lot, because if you deal with applications where the performance and scalability, those two basically goes hand in hand. Your cache can impact your scalability, and if you don't tune or if you don't choose a proper topology for your cache, you might impact the scalability. And in regards to that, you can choose, for example, distributed and replicated, or distributed and partitioned, and so on, depending on your context and how much you want to scale and how performance you want to put in your application. The batching, it's the next one, which basically says that if I do batching, I basically merge a bunch of items inside, I wrap all of them inside one package, and I send them across the wire to a remote, for example, server. The thing is that with batching, we should pay care of the bandwidth and the receiver handler's rate, because we can't scale with the batch size very much. Why is that? Because the bandwidth might be a limitation, and on the other side, we can saturate the receiver. So sending with a high frequency, the sender, if sends the packages with a high frequency, the receiver might get saturated. And how we can measure all the things, it's based on the round trip time. So we have to tune the batch size in compliance with the bandwidth and the receiver's rate to have a constant and the optimal round trip time. And all these parameters are coming into place. Designing asynchronous, it's also a good recipe. Also, Martin Thompson said, design asynchronous by default. Make it synchronous when it is needed. Because if you design asynchronous, you can see here on that graph, during the green period, you might handle other tasks. So once you are notified, you can resume your previous work and handle the response. Of course, probably it's not very straightforward to change your mind and to be focused on designing asynchronous, but it's also a good alternative. I will also suggest, if you can stick with stateless, you can increase the performance and scale even more your applications. What Java does in this design asynchronous field, it comes with some APIs. For example, completable future, it's one of them. Future, it's another one. And recently, with 9, they added this flow in the Java util concurrent package. They are quite interesting APIs. In terms of memory access patterns, because we saw in the matrix example, they count a lot. The way the data structures are laid out in the main memory and how we traverse all of them. Basically, there are 3 categories. The strided one, it's the first one up in there, and it says if I traverse the memory based on a predictable pattern. This one, it's the easiest one from the CPU, from the hardware perspective. If the second one is for the spatial traversal, which says basically the elements closer to me, closer to one that I already requested, supposing they are already in the cache, they are already in the cache as well. So it's likely to refer them in the future. And the last one is for the temporal, where I randomly walk through the entire heap, I request some elements, and there might be a chance in the future to request the same elements again. The thing is that starting with the stripped pattern, continuing with the spatial and temporal, you pay more cost in terms of latency. In case of strided one, you can see there was about 1 nanosecond per operation. It's extremely fast. It means it was in the L1 CPU cache. The second one was for spatial, around 5 nanoseconds, which means it probably was grabbed from the second level, and temporal from the third level. Now, it depends, of course, on the data set you test with. But keep in mind that these memory access patterns have a big influence in the performance you might get. And let's take an example and to compare the hash map with chaining implementation, the one which is default in the JTK, and another one which is based on open addressing. What does the chaining implementation? Suppose you have a data structure, and inside it it's an array, and you place the elements based on the hash code in the appropriate bucket. And so you added the first element, you added the second element, there is no collision in between them. And the memory layout, as you can see up corner, there is no guarantee they are somehow closer. And in case of collision, it's even worse, because in case of collision, it does the real chaining, and now your element could be sparse across the entire heap. Java helps us, especially during a full GC cycle, because during the full GC cycle, the memory might be compacted and they might be collocated again. But the moment you allocate them, there is no guarantee they are collocated. So in this case, we can talk about, and we can stick with a temporary memory access, which is not the good one. It's not the best one. In terms of open addressing, how it works, basically it keeps the same internal structure, the table, and it adds the first one. It adds the second element, there is no collision, no problem. And when it tries to add another one for where is a collision, open addressing has some collision schemes. For this particular example, I was choosing the linear probing scheme. What it does, basically, if there is a collision, it tries to linearly searches through the data structure until it finds, one by one, until it finds a first available slot. Since it finds an available slot, it places the element in there. In this case, the memory, it's more compacted because the chaining, it's not used anymore, the lists are not used anymore, and the performance might be again during the runtime, because the memory, it's more compacted. Elements are collocated. In terms of comparison, the overall comparison, chaining versus open addressing, for the memory, the chaining one wastes more memory. The open addressing, it's more compacted. Nevertheless, the open addressing might perform in some situations a bit slower, especially when you try to add more and more elements and you are closer to its capacity, because it struggles to find the next available slot. So basically, it iterates through more indexes inside that table. So open addressing might be something that you can consider when you have to deal with performance and you want to stick with a hash map implementation. Also, Martin Fowler said the choice of these data structures often makes a big difference, and some of the developers use whatever they are get used in the previous. And it's not quite a good approach. We should always have a wider understanding. We should always understand the data structures, the algorithms. I would strongly recommend you also to read the Ulrich Depper papers. Even if they were written like 10 years ago, everything out of their papers, almost everything, of course, the principles I'm referring here are the same today, because the hardware didn't change so much. And always stick with the data structures, the algorithms. They make a difference. Log-free algorithms, it's another type of algorithms that help us if we are working in the performance field. Why? Because they basically guarantees there is all system-wide progress. In log-free approach, there is no such possibility that one thread can indefinitely block the other thread. And the paradigm in Java for this, it's a compare and swap operation, which basically does what it says. It tries to compare the local variable with the one from main memory. And if I have the same copy, I'm able to update it atomically. If I don't have the same copy, which is the case for the second thread, it fails. And what it does later on, it needs to reread it and try it later on. And this is supported by the hardware. In Java, the API for doing it, comparing swap operations, it's the one from atomic integer, long, and so on. It's it is called compare and swap, but also there are data structures and based on compare and swap, like the atomics, reentrant lock, it's using compare and swap, and there is also a concurrent link queue implementation, a queue implementation basically, which is based on the compare and swap. Cache oblivious algorithms are the algorithms that are not tightly coupled by the CPU and the CPU cache size. And what they do, it's basically they are efficient from the CPU perspective and agnostic on the same time. The way you traverse the data structures and how predictable you are, they help you to avoid those possible cache miss effects. In this category, I would mention the matrix multiplication, transposition, some sorting algorithms. Let's take an example on the object-oriented programming, the thing that we start since the beginning when we start to code. And we learned that doing everything in the OOP, it's a good way. I took this example. Let's suppose I have an account, which is a wrapper over several fields, could be possible other methods. And I have that list. It doesn't matter how it is initialized, and I have a traversal across all the instances, and on each instance I have to check if it is active. If it is active, if it is not active, I trigger an event. But let's see if it is a good approach or not from the hardware perspective. Remember what we have discussed with the matrix traversal. This is the same case. When I say account.isActive, what it does, the account, there is a cache miss, and the account, the object, including the isActive field, it's layout in the CPU cache line. And because we are just asking for isActive, we basically fill in the entire cache line to request just one field, which is very, very inefficient. And that's why another approaches like data-oriented design focuses on optimizing this kind of scenarios, and it reorganizes the data in terms of reads and writes from your program. For example, in this case, to make it more efficient, what I have to do is basically to pack all the Boolean fields inside just one array, and when I iterate through them, just by saying are active, excluding the object header, of course, I have all the others on the same cache line, and when I request the next and the next, they are in the same cache line. So I minimizes the number of CPU misses with this approach of data-oriented design. It is mainly used in gaming industry when the guys are really keen of this kind of optimizations. So they are trying to compact the data and to restructure the code in a very, very CPU friendly manner. The next pattern, the next layer is about operating system guidelines. The first guideline is about thread affinity. What says thread affinity? Basically, in our modern architecture, there are many sockets. Inside one socket, there might be multiple cores. Each cores might have two physical, two threads because it's hyper-threading. And thread affinity says that if I bound my thread to one core on one socket, I will benefit of the caches later on. So in case that thread will be descheduled, there is no chance to be rescheduled on another socket. And this is good from the caches, because if the thread is descheduled, all the caches on the other core, on the other socket, should be moved away. In Java, there are some libraries to do that. One of them is thread affinity. It's not very natural because Java acts at the higher abstraction level. In C++, C, Linux, it comes very easy to do this thread affinity stuff. Non-uniform memory architectures or non-uniform memory access says basically when I have multiple sockets and I try to allocate or read something from the memory, it's always better to stick with my local memory, because if I'm on the core in there on the right part. And if I want to access something from here, what I should do, the thread will pay the stall waiting for that object to be retrieved from the memory. So it pays the cost of the hypertransport or the QPI, and the latency will be higher. There are some JVM NUMA aware collectors. They are working only with parallel scavenger at the moment. So you should explicitly activate the parallel GC or parallel GC in hotspot to benefit of the NUMA collector allocation. There is also a JEP for the G1 to be NUMA aware. But nevertheless, keep in mind that being more NUMA aware, you benefit of the performance because you always try to request memory which is local to you in the hope that next threads will be scheduled on the same socket and they have the memory closer to them as well. Large pages is another one. You can find it under terminology of huge pages. It's basically the same principle. How is it working when you try to do a mapping between the virtual address and the physical address? There is a small cache which is called TLB, which stores the latest translations. Basically, first time when you request something from the main memory, the TLB is searched. If the translation is in the TLB, it's fine. But if the translation is not in the TLB, you have to go into the page table. And the page table walk, it's costly. That's why it's advisable to reduce the number of page walks. And here are two solutions. There is no other option. It's either increase the TLB to store more translations, either to increase the pages in the main memory. The first one, unfortunately, is not quite an easy one because the TLB should be fast. Increasing the TLB, it slows it down. So the second one comes and says, okay, instead of using pages 4K in the memory, let's use huge pages or bigger pages, 2 megabytes, 2 gig, and so on, because if more virtual addresses mappings will fit in the same page, and we will minimize the number of TLB misses. In Java, for this, it's the option called use large pages. You can activate it, but you can also have the OS support. If it is not activated in the OS, it doesn't work. Solaris comes by default. It's activated by default. In Linux and Windows, you should explicitly activate it. And for us, for the majority of the programmers, there are hard guidelines where the large pages are useful, because the question might arise, okay, large pages it's something useful, fancy, but how should I know when to activate? How can I be conscious about that? And the guideline is that large pages are suitable in context of intensive memory applications, and those applications are based on the large contiguous memory access patterns, because otherwise they are not quite handy. And as a consequence, if you do a profiling and you figure out that the number of TLB misses and it's higher, and you pay a significant cost in the page walk, you can how you can get them based on hardware counters. So you do a profiling at the hardware level, and if is that context, if it is that case, there is a clue that you might enable large pages and retest it again. Nevertheless, large pages are not recommended all the times. For example, if you have a small working set and if you have a large working set, but that memory it's very, very sparsely used. For example, some databases don't recommend enabling by default transparent huge pages, which is basically the same as huge pages, and they explicitly state in the specs that please disable, because they are not get used. They don't benefit at all about this. So it's something that you might test on your side and to decide if it is good or not based on the nature of your application. If you have a lot of I/O operations, quite intensive operations, it's always better to stick with RamFS and TempFS. Never go to the physical disk. Why? Because I did some tests. I used my HDD, my SSD, and RamFS. And RamFS for read and writes in terms of throughput, it's about one order of magnitude higher. So it's incredibly, incredibly fast. Even SSD, it's fast, but in comparison with RamFS, it's slower. Also, you can notice in here that the reads are quite high. That's because when I did those tests, the effect of buffers and the caches in Linux came in place. So I couldn't avoid that. Even if I tried with 8 gig and I tried to sequentially allocate in my test this 8 gig in chunks of 4K or 512 kilobytes. The second level and the last one is in terms of hardware. The first one, it's also very well known and well discussed, the fault sharing. Fault sharing, it's basically a CPU issue. It's the way caches are built inside the CPU. And we should be aware of that, and we should avoid this fault sharing situation. When it might happen, for example, you have one instance, let's say fault sharing, a shared instance, and there are two fields in that instance, X and Y, for example. And you have two threads which shares the same instance, and one thread, at least one thread, tries to write something, and the other thread reads. The condition must be at least one should write, because if both of them are reading, you shouldn't care about fault sharing. And what happens in case of, for example, in here, I set both of them writing. They are scheduled to different cores, for example, and if one updates the value, let's suppose this one updates X, it invalidates the other one's copy. If the other ones try to update Y, for example, it needs the latest copy which was updated by the second one. And there is also a request for ownership situation, because you need to get the ownership before updating it. And there are a lot of messages, they are called requests for ownership messages, between switching between these two threads, from invalid to modified and so on. So this fault sharing impacts a lot. And the guidelines around fault sharing, what are the patterns for the programmers to be conscious about fault sharing? It follows these steps. When you have variables sitting on the same cache line, so basically they are one next to each other, closer enough to fit in those 64 bytes on the same cache line. And when you have concurrent access, but it's not enough, you need at least one writer thread, because if you don't have at least one writer thread, if it is only reads, it's fine. And there is one more: the frequency of writing and reading should be high, because if the frequency it's not high, you read something and you write it later on, there is fault sharing, but you don't notice it, because the frequency it's not high. It's on the contrary, it's lower. I did some tests. Java comes with this annotation contenting. There are many ways to distribute the fields X and Y, to don't collocate them on the same CPU cache line. And in terms of baseline, the base one is 3 times slower than the contented. Why? Because there are a lot of messages, there is a lot of battle for the ownership, and so on, the things that we have discussed. So it's a recommendation to be aware of such situations and try to avoid them. Zero-bit recording, it's a technique mainly used for the hard disk drives. Basically, how they are built, in the outer tracks have more sectors. This is a physical aspect. And because the outer tracks have more sectors, there are more bits stored on the outer tracks. For example, you see here on this yellow one, there are 8 sectors per track, and the last one there are 16. So it's normal there are more bits per track. And because of that, the throughput, it's higher when you read and write data for the outer tracks. When you buy a new HDD, it tries always to allocate from the outer to the inner. That's why you'll have a better performance. And once you install the OS and you try to copy on top of it other files, it slows down the performance. In terms of solid state drive, the things are different because it's another technology. And from the performance standpoint, I recommend you to enable trimming. Trimming basically says that once I remove something, they will be physically removed at that moment. If the trimming is disabled, they are not removed at that moment. They are just marked as being cleaned. And later on, when you try to write something, because the SSD can't write unless it cleans the entire block, you have to wait until it cleans first the entire block. If you enable the trim for the first very beginning, the block it's clean. So you don't pay this latency at the moment you try to write. The OS scheduler, it's another recommendation. I did some tests for the OS scheduler. We'll see right in a moment. And also enable write caching. This is enabled by default, to my knowledge, but it's always better to double check it. Let's get back to the I/O schedulers. In Linux, I did this test on Linux. There are basically 3 schedulers. The default one on my case was Deadline. There is another one called NUP and CFG. This one stands for fairness. This one is mainly suitable for HDD, but not SSDs. If you have an SSD, and if you have Linux activated and you have a higher rate for write and reads, it's better to also activate NUP, because this one, based on my tests, became better. There is not a quite big discrepancy between NUP and Deadline, but in any case, if you want to be very fast and the best performance, the NUP I/O scheduler, it's good to enable it. And in terms of trimming, I did the same test, but this time I activated the NUP scheduler, and I used trim on and off. And in case of trim off, in case of trim on, sorry, I got a bigger throughput for the read and the write. So which concludes me that if you pay care of the I/O scheduler, if you take the best one, and if you enable the trimming, you will get the best throughput in terms of reads and writes out of your SSD. C-states are also known for idle states. What CPU does, basically it reduces the cycles, and it saves the energy, because this is the clue, to save the energy at the end. The states starts from 0, ends to 6. There are also intermediate states, one that are extended, and so on. Nevertheless, when it goes to the higher one, the highest one, it reduces the clock frequency. The thing is that you pay more the cost to warm it up again when something is scheduled. So the warm-up phase takes more time until it reaches again the best performance. And in terms of that, it's better if you want a steady throughput out of your CPU to consider disabling these states, because you will consume more energy, that's for sure, that's no debate in it. But your CPU will be more steady, especially if you are doing, for example, performance stats. It's also good to lock the CPU frequency to the highest rate out of it. So getting back to my initial latency model, in regards with what have discussed until now, the bottom one, where you don't have performance as an architecture significant requirement, stick with the clean code, stick with cyclomatic complexity, minimize them, have good cohesion, reduce the number of abstractions. This applies for all projects. You can see them as built-in. if you have an affordable latency, maybe you have to take care of data structures, the complexities. You can take batching, you can take caching. There are, for example, caching, it's very cheap just to properly tune it, as we discussed. Things are interesting if you are touching the low latency, because in low latency, you have to take care about how you iterate through the memory, what are the patterns. You might deal with lock-free, with asynchronous. You may choose, for example, stateless. You may choose RamFS or TempFS. In low latency, you might tune as well the garbage collector for Java as well. You might tune it in terms of GC itself, the collector, but also you might tune the heap, metaspace, and so on. And also, you have to take care of the object lifecycle, the frequency, if it is frequently created, the promotion, over promotion, and so on. And the last one, on the last layer, I put thread affinity, NUMA, large pages, fault sharing, data-oriented design, why not? And you have to take care of the caches. Here, it's a remark that this model, it's based on my interpretation. It's not exclusive, and it might be subject of changes. In closing, I'd like to end saying that the performance is simple. You just have to be aware of everything. So we iterated through a lot of layers, a lot of principles, guidelines, tactics. Thank you very much. Thanks. Here, few links if you are interested in documentation as well. Yep. And if you have questions. Sorry. Yep. Not very often. I'm mainly used I'm working in finance applications, and I'm touching the low latency. The ultra low latency I didn't touch. Okay, thank you very much if there is no other questions.